Okay, and quick record here. 1, 2, 3. Nope, not on here. Sally's not here. Just because everybody is bound to ask, it appears that Ryan has dropped, so he won't be coming. Also, Anne, have you made arrangements or whatever with registrar? Okay. Let me talk to you after class. We can figure out what's going on there. Well, so I can figure out, you know what's going on. Okay. So, finishing what we were doing at the end of last class period. Solving a problem using Coulomb's law to find the force between a point charge out here and a wire that has charge distributed over it. So in doing that, the first thing I did was I had charge distributed over a wire. So that was a linear charge distribution. So I had specified that my dq, the charge distribution, was a one-dimensional charge distribution. So I had, well, maybe I didn't have it. dq was equal to lambda ds. So that was the first thing. The second thing was I choose a little ds here that has charge dq, and I find the force vector between this point charge q1 and that little piece of charge dq, and so that's what this equation was, minus k q1, then the lambda ds, whoops, that was the wrong place. The lambda ds was my dq, r hat along with the minus sign is what gave the direction, and over r squared. And then I said, but now I need to integrate this up, and if you look at this, I have ds and r as two different variables. S is the distance along that wire, and r is the vector from charge 1 to charge 2. Right? Those are two different variables. They're not going to stay constant. That's what makes them variable. Just in case you lose track of what makes it a variable. So I have two things that aren't going to stay constant. In order to do the integral, I need to get it down to 1. Now, most of us would have said, well, let's integrate over s. Because I have a wire that starts here and ends here, that's pretty simple. But the integral actually turns out to be easier if we define a new variable, theta. And so in my picture, I didn't draw it, but theta was this angle here. And so I wrote this, of course, before class last period, the sine and cosine and tangent definitions there. And using those definitions, I was able to change it over to theta. Now, a reminder, I should ask Toussaint just because that would be evil. Why am I changing to a variable that's not even in my equation? Okay, it's easier was the answer I gave. Now, how would you know it's easier beforehand? You wouldn't. Why would you even want to talk about the angle? Well, the angle does come up because we have to break our force into components, the x component and the y component. We integrate the two components separately. And so to break them into components, the component of the x direction will be the magnitude of the force multiplied by cosine theta. And actually, I shouldn't have put the magnitude sign here because that would take away minus signs. I put the magnitude there just to emphasize that it didn't have direction, but it's actually important to keep the minus signs. I wasn't thinking it through. So I'm going to take this thing up here and then the cosine theta to get how much it is in the x direction, and this thing up here, sine theta, to get in the y direction. Now we do have all three variables, right? If I expand this out, I have this. And so there I do have all three variables in there. So now we know we have to do something with the angle. And like I said, it's going to turn out that doing it with the angle is the easiest. So then we had to go through and make our conversion. How do we convert things to the angle? And I really only went halfway through that last class period. I said, well, when you look at these definitions of the trigonometric relations, it doesn't stand out, but it's the tangent theta one that makes the simplest conversion. Now, if we look at those definitions, sine theta is y over r. Well, the y part is going to change, and the r part is going to change. So both the y and the r are changing. That's probably not going to be the best one to do my conversion of variables. The next one, cosine theta is equal to x over r. Well, x is a constant because that's the perpendicular distance to the wire. So there's only one variable on the right side, and you might say that's the one to use because it only has one variable. And after all, it has cosine theta, which is much more friendly to me than tangent theta. But through trial and error, and trust me, the first time I did this, it was a lot of trial and error because tangent theta was the last one I tried. Tangent theta is the one that gives you the simple conversion. So you take tangent theta. Now I have ds. And so I need to get something that's going to have a dy, since dy is equal to ds. So I take the derivative of both sides. So the derivative of tangent theta is 1 over cosine squared theta. How do I know that? I only know it because I needed to know it for this problem. It's not one of the standard things I memorized when I took Calc 1. And so the derivative of tangent theta is going to be, I'm going to erase that and just put it here. Since ds is dy is pretty obvious, just put it like that. If I do this derivative, d tangent theta is equal to d theta over cosine squared theta, then the derivative of tangent theta is d theta over cosine squared theta. Doing the right side, derivative of y over b, or y over x, whichever way you want it, since x is a constant, that's why I put the y over b, is going to be dy over b. And so there I have the conversion I need. My ds is equal to dy is b d theta over cosine squared theta.
Wait,
So, go ahead.
What do you mean by connection? D theta over cosine squared theta is equal to dy over b?
Okay, this equation here, basically just cross multiply. Actually, just multiply both sides by b is what I did. Multiply this by b and this by b, and then those cancel.
No, but how did you get to that equation?
Oh.
Why is d theta cosine squared theta equal to dy over b?
Okay, let me just erase the parts that go in there and do it again then. So those are the parts that go in there. So what I did is I did the derivative of tangent theta is equal to y over b. Right, since I had this equation right here, tangent theta is y over b. I'm taking the derivative of that.
Okay.
Now this is a generalized derivative, not a derivative with respect to something, but a generalized derivative. And so that becomes,
Okay, and that makes sense to me. I guess I didn't realize that you just took the derivative of that whole equation.
that, and then using the definition of the derivative of tangent theta, which I erased to give myself room to put this back in here, derivative of tangent theta is 1 over cosine squared theta, but since I'm not doing it with respect to theta, I'm just doing the derivative, I'm left with a d theta. And on this side, it's just going to be, I'm left with a dy. And so then I multiplied both sides by b. So now let's see where that gets us, continuing on stuff that we haven't written down before. Where that gets us now is, I didn't want that color, dfx is equal to minus kq1 lambda, and then instead of ds, I'm going to put in b d theta over cosine squared theta. So this parenthesis is what the ds was before. My cosine theta, and then divided by r squared. Well, if you look at this, and you have any sense at all, you say, you still have two variables in your equation. Everybody see that? I have cosine theta, and I have r. So I need to relate the two. Well, since I have r and cosine theta, the quickest thing is going to be to use the relationship between r and cosine theta. Now remember, x was a constant here, which I'm calling b. And so using this relationship, what is r? So I'll substitute that in. So this is now going to be minus kq1 lambda divided by b over cosine theta quantity squared times b d theta over cosine squared theta cosine theta. Now we can collapse things. Because notice I have b over cosine squared theta, b squared over cosine squared theta. If I divide those two, what am I left with? Yep. And so I'm left with that. So now it becomes a much simpler looking minus kq1 lambda over b times cosine theta d theta. That's an easy thing to integrate. So that's dfx, which means that fx Now I have limits on this, right? I have limits on my angles. And so I'm going to put here from theta initial to theta final. And after I do the integral, which of course is a one-stepper, then I will look at how those limits play in. So if I take this, and I have to first copy it so I can put it on the next page. Apparently I'm going to copy it with some other junk. Okay, if I do that integral, of course, what is the integral? Integral of cosine. No, she's right. I was doing that in my head to determine if it was plus or minus. I believe she's right. So I'll have my minus kq1 lambda over b out front, and then I'll have sine theta going from theta initial to theta final. Well, you know what the easiest thing to do to evaluate those limits is to look back at my initial picture and just determine what sine initial is and sine final is. Right, because one of them is going to be a over, well, actually it's not that simple. It's a over the square root of a squared plus b squared. Right, because sine is opposite of hypotenuse. So I'm going to have sine theta initial is equal to a over square root of a squared plus b squared. And sine of theta final is equal to that. And so then I put those two values in, and I have my final answer. Now, for your homework problem, you're going to be going from an angle of 0 degrees to 90 degrees. Because your homework problem is a semi-infinite wire with your position starting beside the top of the wire. So that means you're starting at 0 degrees, then you're ending all the way down there at 90 degrees. So if your homework problem, it comes out simpler not having these crazy...
Where is this homework?
On Moodle. And so I have to put my sine theta final, my sine theta initial stuff in here. Yeah. And so I put the stuff from before. Now if I want to do the y component, what's different about the x component and the y component? Yeah, sine instead of cosine. And so it's going to be all the same except for sine out here for the, it'll be an integral of sine for the y component instead of an integral of cosine, which means when you do the integral, it'll be minus cosine inside. So the completion of you just have that integral. And of course, that gives us that. And I would go back and I would just say, okay, so what was cosine in the initial and what was cosine in the final? Question?
Well, there would be a negative on that one, right?
I dropped the leading negative sign.
Okay.
Yeah. Maybe I should have said that.
Makes sense.
Yes. Okay, so the first homework problem has two pieces. Now, notice that there's one A, Roman numeral I, down to like V, right? So there's one A, 1 through 5, and then there's B, 1 through 5. And it has specific requirements like draw the picture using a ruler, draw the direction for the electric field, and give your reason why. Make sure you put Roman numeral 1 and put all this stuff there. Roman numeral 2 and put all this stuff there. It asks you, like, what ideas are you going to use? Well, what ideas are you going to use? For problem 1, I've already told you, you're going to have to use Coulomb's law. For the other ones, I'm not going to tell you which one to use. But for the first one, you're going to use Coulomb's law. You're going to do it like we did here. If you can do the problem I did right here, if you follow what I did, it's much simpler doing 1b, because this is like 1b. 1a is easier than this, that's why I did the one like 1b. So we're going to use Coulomb's law, but what is different from what I did here and what's in the homework? I know one student at least has started it, probably more, but one has come and talked to me. So Tori, what's different? What was the thing you came to ask me?
They wanted electric field strength rather than the force.
Right, they want electric field rather than force. What's the relationship between electric field and force?
Electric field is force over Q, like the little Q, not the big Q.
Electric field is the force divided by Q is the way we write it. Well, in this problem here, my Q would be the charge at the point where I was finding the force, so the Q1. So when you're doing the problem, you just start with the same Coulomb equation, except for you say, this is equal to minus K Q well, I got to put D's in front of these to make it so we can do our work. So minus KQ dQ R hat over R squared, all divided by, and I have to use the same subscript as I used for that one. In fact, let me change the colors on those just to make it really clear.
So it just removes the constant. That's all.
That is all. It's just I want to make sure it's very clear to people what it's removing there. So we're dividing out the green parts, and we're left with the equation that you're actually going to use is minus K dQ R hat over R squared. So that's just dividing out a constant of the problem we did. Hence, all of the math is the same. We just divided out a constant. Now, if you have questions about how to do that first problem, please feel free to come and ask questions. In fact, for any problem, but the first problem is the one we can do right now. After today's lecture, assuming that I finish in time, then you'll be able to do at least half of them. So that brings us to Gauss's law. Now, Gauss's law, sadly, is not in our textbook as far as I can tell. I was looking for it, couldn't find it. But Gauss's law is a fundamental part of electromagnetism. Gauss's law is really a different statement of Coulomb's law. It comes from the same origin. I think our textbook just decided we'll stick with one of them. But Gauss's law is really the one that makes more sense, at least to me. So let's go back to when we talked about drawing pictures of charge. I had a little charge here, and let's say that following the sign conventions, this is a positive charge. What can you tell me about the electric field lines for that positive charge? Okay, electric field lines go out of the positive charge. How is it that you know they go out?
Theoretically thinking about the test charge and the source.
That is the correct answer. If you were to put a positive test charge out there, the direction of the force on that positive charge is the direction of the electric field. But then there was another thing. How do I know how many lines to put around that dot?
It's arbitrary.
Arbitrary but proportional. And so if I had more charge, I'd have to have more electric field lines coming out. Less charge, less electric field lines coming out. So that's where Carl Friedrich Gauss, and notice how we pronounce his last name, Gauss. So many times I've heard people say Gauss or something like that. I've never figured out where they get Gauss from that, but it's Gauss. Okay, so he realized, wait, since these electric field lines are, the number of them is proportional to the charge, then let's look at my picture here. If I were to just take a box, to make a box here, and count how many lines go out of that box, that would tell me how much charge was inside. Now this is a two-dimensional picture, but of course, to be careful, you really need to do it three-dimensionally. That is, you have to make a three-dimensional shape. You measure all of the electric field lines that come out of that three-dimensional shape, and that has to tell you, based on the arbitrary constant you used, how much charge was inside. So that's his basic idea. If I measure how many lines come out, I know how much charge is inside. If there is no charge inside, like if I put it like this, I have the same number of lines go in that came out. It doesn't matter what the shape of my box is as long as it's completely closed. If it's not completely closed, then we're going to have a problem because we could have some electric field that went in or out, the parts I wasn't counting. So now, that's the idea of Gauss's law. The actual practice of Gauss's law is, of course, a little more mathematically intricate than just the idea. So the actual practice, we have to talk about this thing called flux. Flux, as far as I know, flux is a shortening of the word fluctuation. How does fluctuation deal with this? I really don't know. But the electric flux is a measurement of the electric field strength parallel to a surface. I say parallel to a surface and I'm wrong. Normal to a surface is correct. Wow. At least I corrected myself quickly. So if I have a surface like this tabletop here, and I have electric field that's parallel to the tabletop, none of it's coming out. And so the flux would be zero. There's nothing coming out of it. But if I had electric field of the same strength that was pointing this direction, then I would have just the magnitude of the electric field multiplied by the area to give me the flux. And of course, if I'm somewhere in between, how can I get the flux? Let's say, for instance, here's my surface, and the electric field is going at some angle like, how do I find the flux, the electric field going through the surface?
Trigonometry.
Yeah, trigonometry. I just need to find the component of the electric field that's normal to the surface. So we have a picture here showing basically the same thing. And what we do is we identify the direction of the normal to the surface. Notice the words there, normal to the surface. And then we find the angle between the electric field and that normal. Which part, sine or cosine, gives me the part that is going to be going through? Cosine. And so we say, if I have a constant electric field, that the flux, and we use a symbol for flux, a capital phi subscript E to say electric flux, because later on we're going to have magnetic flux. Usually we don't put electric flux here, we just, when we get to magnetic, we say, okay, we have a new flux, better put a subscript on it, is equal to the electric field times the area times cosine of the angle in between. Now you and I, being more educated students, can find a better way of writing that. Instead of E times A times cosine theta, what's the more common linear algebra way of writing that? Remember, E and A are vectors. A is the vector. Maybe I said remember, but you didn't know that A was a vector, did you? A is the area vector that's direction is the direction of the normal to the surface. So E is the electric field vector. A is the area vector whose direction is normal to the surface. What combination of E and A gives you a scalar with cosine theta? Yeah, you're not remembering. The electric field dotted to the area. The dot product, the scalar product, gives you the amounts that are parallel. And that's what we're looking for here, is how much electric field is parallel to the normal to the surface. So that's the mathematical way of finding the flux. So now we can get into Gauss's law in its full beauty. Oh, actually, it's on the next slide. They have the full beauty. For a closed surface, then, this is not for a closed surface. This is just the relationship I had on the previous page. E dot A, if you're doing it for a surface, then you have to integrate over the surface. So I have the integral of E dot dA. Why E dot dA? Because I'm integrating over the entire surface. This is a two-dimensional surface for a three-dimensional object.
So you're essentially saying if you had an uneven surface, that would be what that's for, or what?
Well, this is for I have a three-dimensional object. Like I started with the idea of a cube, right? And so I would have to do the integral over each face of that cube. So the cube's a three-dimensional object, but my integral is only over, if it's on this side, it's going to be x and z, this side, x and y. Right, because area is two-dimensional.
Yeah, no, I get that part. I'm just trying to figure out. You kind of started with something that was not an integral. You switched to an integral.
Right.
You're saying, like,
well,
in the case of a standard.
If I have a changing electric field and I'm measuring how much electric field goes through the area of the surface, because the electric field's changing, I can't just multiply the two. I have to take the electric field here times this amount of area and the electric field here times this amount of area, and the directions as well to get my how much goes through.
So if the electric field is changing, wouldn't that be the D? Like, wouldn't it be DE times A?
The electric field is changing, but when I do the integral, because I'm doing it over the surface, not over the electric field, right? I'm not doing it over everywhere the electric field exists. I'm doing it only where the electric field is going through the surface. So that's why it's a dA. Okay, now, if I have a closed surface, going back to my previous picture, if it was a positive charge, was the electric field going out of the surface or into the surface? Out of it. And so that, with this equation, is a positive flux. So if you have a positive flux, you have a positive charge enclosed. Negative flux, negative charge enclosed. Positive flux means that the electric field is coming out of the surface. Now the full beauty of Gauss's law. What does this here mean? Electric flux. Just making sure you remember the symbols. What is the name for that character? It's a capital phi, or you can say capital phi. Most people say capital phi. That's the Greek F for flux. You can see how they chose it. This other part here, this here is the part we usually use for the other side of the equal sign. This is an equivalence since we have 1 over 4 pi k is equal to epsilon 0. So those two are equivalent forms. Why do we show the two different equivalent forms? Because this here has less to write, and that's why we usually use it. But this here has the constant that we usually use in Coulomb's law. So we can relate the two and see how it all works out. This Q enclosed, that's just the charge enclosed like we started talking about. That epsilon sub 0, we've already learned the permittivity of free space, that is the constant of proportionality between how much charge is enclosed and how many lines we drew. Right, I said it was arbitrary. Well, in truth, for our picture it's arbitrary, but for real life, that's the constant to relate the two. So, here is Gauss's law. This is the non-calculus way we write it, and this is the calculus way we write it for the flux. So everything that is left of these marks is saying the flux equals. Question?
What's the little circly thing?
Getting there. Getting there. So what's the difference in the algebra version and the calculus version? Here's the algebra version, and here's the calculus version. How do those two symbols relate? Imagine there's no circle on there. How do those two symbols relate? Okay, one is summing over finite pieces, and one is summing over infinitesimal pieces. So they're both summations. And then we have E dot A. I have a mistake here. I didn't even notice it. You really have to have a D to have a working integral. Integral of E dot dA. We have the dot products for both. We have the dA and the A. The difference is the algebra one can only be used if you have surfaces that have fixed relationships. The calculus one can be used on any surface. Now here's the fact you're going to love. This can be really, really hard unless you have a nice, simple symmetry. So we're only going to use it, we're calculus class, so we got the calculus form. We're only going to use it in the situations where it collapses down to the easy form. So you're the calculus class, you can understand what that symbolism means, but we're only going to use it for simple cases. So I'll still be writing the integral sign because it's more accurate and it says more of what I'm doing, but it's going to come down to algebra. Now to the question that Tori asked. What is that little circle? No. I'm glad that you took a shot. The key to that circle is, where does it end? Okay, it doesn't have a hole. That's why they use it. It's the integral over a closed whatever. So in this case, since it's dA, it's the integral over a closed surface. You can't have any holes in that surface. That's what that means. So in your doing of work, it's just an integral. But it has meaning because it says it's over a closed surface. There's no openings in it. If you have a line integral, right, if it was dl, then it would be a line that comes back on itself. In which case the circle would be more meaningful because, well, that's exactly what happens with a circle. And if it's a volume integral, of course, I don't know how you do that. You'd have to have some way of defining a higher dimension, I think. So now the slide that I showed Tori when she came and asked me, now that we've looked at Gauss's law and we've looked at Coulomb's law, how do we decide which one to use for things like our homework problems? And it comes down to symmetry. If you have what I will call an exploitable symmetry, then the problem is going to be easier using Gauss's law, so use it. If you don't have an exploitable symmetry, it's going to be harder using Gauss's law, so use Coulomb's law. So Coulomb's law is the easier one for some generic random distribution of charges, but for something that is a nice symmetry, and I will define what makes it a nice symmetry, then Gauss's law will be the easiest one to use. So use Gauss's law when it's easier. Don't kill yourself when it can be easy. So, of course, at this point, you have no way of deciding what's easier and what's not. So let's start with the simplest problem you can. What is the flux through a sphere of radius r equals 5 centimeters that has a point charge of 2.0 minus 2.0 microcoulombs at its center? This didn't have to be so specific for me to get the proper answer, because what does Gauss's law say?
That the flux is equal to the outside. It's on that side, yes. Sorry. The flux is equal to the enclosed charge over the 4 pi k, which is,
Well, over the permittivity of free space. Just
what's it called?
permittivity of free space.
Right.
Epsilon 0. Okay, so it says the flux. What I'm looking for is just equal to the charge enclosed divided by epsilon 0. So I can take this and I can answer right away. The flux is equal to charge enclosed over epsilon 0 equals minus 2.0 microcoulombs over 8.85 times 10 to the minus 12 Newton meters squared per coulomb squared.
Well, what?
Those are just the, actually, are those the units? No, those aren't the units. Those are units of K. No. It should just be, just invert that, coulomb squared over Newton meters squared. So,
That's 4 pi k.
this is 1 over 4 pi k. Yeah.
Oh. No, all right.
So now we can do that math. I don't really care to except for one thing. What are the units of flux? Now, if instead of doing it that way, I had done it the other way, I have the electric flux times the area. Or excuse me, the electric flux is electric field times the area. Electric field is force per charge, so Newton per Coulomb. And then I multiply it by the area squared, so Newton times meters squared per Coulomb. Two different ways to arrive at the units, make sure we got them right. And I mean, anyone can put that in their calculator to get the number, so I'm not really concerned about the number. Now, that was just finding the flux. What if I had asked you then, instead, to find the electric field?
Divide out the area.
Okay, now dividing out the area is more complicated than the way you make it sound. We have the flux integral of E dot dA. E dot dA is simple. Change color. What conditions would make E dot dA simple?
If they are parallel or perpendicular.
Okay, I'm going to start with if the electric field is perpendicular to dA, then E dot dA is 0. That clearly is simple. So that is one of our exploitable symmetries. If we can find a surface where E dot dA is 0 because they're perpendicular. Second case, you said parallel. If E is parallel to dA, then E dot dA is equal to EdA, where I dropped off the vector signs because they're parallel. So I'm going to look for conditions where either the electric field is parallel or perpendicular to the electric field. Then I'm going to go one step further. I want and E is constant over surface. Those are the situations I want. Either electric field is perpendicular to the area, in which case the flux on that surface is 0, or it's parallel and the electric field is constant on the surface. So now if I look at a point charge, I have a point charge here. What kind of surface can I make that encloses it that is either everywhere perpendicular or everywhere parallel to the electric field? A sphere. Because my electric field is radially symmetric, then if I put a sphere that is concentric with that point charge, then everywhere on the surface of that sphere, wrong button, everywhere on the surface of the sphere, oops, I get carried away. The electric field is perpendicular to the surface and it's the same strength everywhere, or normal to the surface, and the same strength everywhere, so that I'm going to have E dot dA is equal EdA, where E is constant, so the integral of E dot dA just becomes the constant times the integral of dA. Because E dot dA, E is parallel to dA, then it's just E times dA. And because we're constant distance away, the symmetry requires, right? It doesn't matter what angle you look at a point. So the symmetry requires that the electric field has to be radially outward or radially inward, and it has to be the same magnitude at the same distance away from that charge.
But wouldn't it be perpendicular in this?
It's normal to the surface.
Right.
Normal is the three-dimensional word for perpendicular.
Yeah.
But dA is defined as the direction normal. So E is parallel to dA because dA is normal. Right? The direction we assign for the area of the surface is going out of the surface.
Say then E was supposed to be perpendicular for flux to dA in order to mean anything. So
We need the electric field directly coming out of the surface.
right.
I'm just making sure what your words meant.
Yeah,
by
that's why I
using-
was confused when you were saying earlier that it was 0 if it was perpendicular. I was like, but doesn't it have to be?
Well-
that makes sense because dA is
Yeah.
defined as-
Yeah, so if electric field is perpendicular to dA, that means the electric field, in this case, the electric field would have to be going in a circle. Okay, so now this becomes easy because I have a spherical surface because it matched my symmetry, and that gave me the electric field was constant over the surface and always parallel to dA over the surface. I get this E dot dA, or E times the integral of dA. What's the integral of dA over the closed surface of a sphere? Just go with definition if you don't know the answer. The surface area of a sphere.
4/3 pi.
It's actually 4.
Yeah, that's what I was saying.
So what we have is the electric field times 4 pi r squared is my flux. So now if I take Coulomb's law, I can, or not Coulomb's law, Gauss's law, the flux is equal to the charge enclosed over epsilon 0. That gives me electric field times 4 pi r squared equals charge enclosed over epsilon 0. We'll solve that for electric field. I have that equation. And that should look really familiar because 1 over 4 pi epsilon 0 is K. So what I have is that the electric field is equal to K Q enclosed over R squared. That's the equation for the electric field due to a point charge from Coulomb's law. Hence you can see here now that Coulomb's law is really just Gauss's law for a point charge. Now, in use of this equation of Gauss's law, whenever you're going to use Gauss's law, you always find the left side of the equal side independently from the right side of the equal sign. Some people try to take like one side and just say the other side's equal to that, giving you the simplistic form that says Q equals Q. Right? It's not going to help you solve anything if you just say Q equals Q. You have to actually calculate the flux and determine the charge inside. So usually you're using it to find either the charge enclosed or what the electric field is. And you do the two sides separately and then find the variable you don't know. Now I am out of time. I guess you will get non-calculus explanation for everything else on this. One thing I have to point out. Remember we talked about the difference in insulators and conductors. Insulators, you can have charge distributed through it, so it's not zero net charge inside. For a conductor, the net charge inside is always 0. So you have like a problem that says, so you're not even going to worry about answering this question. It'll come up tomorrow anyway. You have a problem that says that you have a charge density, some function of radius. It's going to ask you how much charge is enclosed in a sphere. How do you find the charge enclosed if you have this charge density? No. We're going to need to integrate the charge density times dV. Now that's a three-dimensional integral, right? Or you could just say that because I'm giving you a spherically symmetric, I'm giving you, the UNL professor gave you actually, then you can say dV is equal to the equation for the area of a sphere times dr. And we just saw the area of a sphere is 4 pi r squared. And so you can just say dV is 4 pi r squared dr. And so my rho is 4 pi r squared dr time, or my charge enclosed is integral of rho 4 pi r squared dr. So you can do that calculation. Then it's going to ask you for the electric field. And you're going to have to find the electric field inside the conductor as well as outside. Inside the conductor, remember Gauss's law didn't say anything about the charge outside. It only said that the electric flux going through a surface is proportional to the charge inside. As long as you have a symmetry where the electric field lines are going to still be normal to the sphere, you just use that and you say, okay, let's calculate how much charge is going from 0 to A, how much charge is enclosed by that, and then my other side, the flux, is going to be the electric field at that distance times 4 pi radius squared. And then you just do that, and you can find the charge or the electric field as you go through the object. Once you get outside the object, you have to change your integral, because now your charge is fixed. It's not adding charge as you go further out. So you're going to use this equation. I don't remember if there's a cylindrical one on the homework set or not. Since we're already 3 minutes over, I will address that at a later date if necessary. We will talk about it in class tomorrow for everybody. I'll see you in lab. Remember, lab today, what are you doing?